Okay, on the last video, you learned to do probability with normal curves as normal distribution. But you know, like we've talked about, all data is not normally distributed. Okay, lots of data is, like IQ scores, weights of men and women, and so forth. But like, for instance, I doubt the ages of MC students. I doubt that that's normally distributed. Okay, so, but here's what is true. Even though the ages of MC students is not normally distributed, I could say, go to the registrar and say, could you give me randomly select 50 MC students and their ages? And I could calculate the mean of that group of 50, you know, and get a certain number. And then calculate the mean of another group and get the mean of that group. But we'll talk about in a minute when I pull this PowerPoint up. But the strange thing is, though, the averages of those groups would probably be approximately a normal curve, even if the individual data didn't follow a normal curve. So let me kind of share this PowerPoint with you, I hope, and we'll kind of talk our way through it. Okay, so we're going to talk about something called the central limit theorem. Okay, so the central limit theorem basically deals with averages of groups. Okay, so it doesn't deal with individual things, it deals with averages of groups. So we've talked about this before, but all data is not normally distributed. Like we talked about, averages of MC students probably isn't. But even for data that's not normally distributed, the means or the averages of groups can be approximated by a normal curve as long as the group sizes are bigger than 30. All right. So look what it says. This is kind of what I was talking about. Ages of MC students are probably not normally distributed. If, however, I randomly selected multiple samples of 50 students each, and I found the mean ages of each of those groups, the mean ages for the groups would approximately be a normal curve if I graphed it. So like maybe I went to the registrar's office and I said, you know, give me 50 names of MC students, and they gave me 50 names and their ages, and I averaged up those 50 ages, you know, added them all up, divided by 50. Maybe I got about 20 3/10 years. Then I went back to the registrar and said, do it again. You know, mix them all up, give me 50 more ages of students, and got an average. Maybe this time the average of that group was 19 8/10 years. And I did it for a third group, and their average age was 20 7/10 years. And maybe a fourth group, the average age was 21 1/10. And I did that repeatedly over and over. If I looked at those averages, 20 3/10, 19 8/10, and so forth, they would approximate a normal distribution. Okay, so central limit doesn't apply to individuals, it applies to means or averages of groups. Okay, now these are kind of your requirements if you're going to do central limit. Okay, if you're not sure that the original data is normally distributed, like you don't know or you're not positive, then n bigger than 30 means that your group size needs to be bigger than 30. So the central limit theorem does not apply to a group of like 5 people or 25 people if the original data is not normally distributed, like with our ages of MC students. Notice, remember that my size was 50 people in a group, not 5 people in a group. Okay, now, if, however, the original data is known to be normally distributed, then the groups can be any size. Like we know IQ scores are normally distributed. So if I went and grabbed 5 IQs at a time and found the average of those 5 IQs, those averages would also follow a normal curve. And the reason my group size wouldn't have to be bigger than 30 is because my original data for individual IQ scores are normally distributed. Okay, so 2 possibilities. If you know for sure that the original data for individuals is normally distributed, the groups can be any size. But if you're not positive that your original data is normally distributed, then your group sizes need to be bigger than 30. Okay, now, how do you use the central limit theorem? All right, basically, it's exactly what you did before in a regular normal curve with one extra step. The mean for groups and the mean for individuals stay the same. Okay, so that's what it means about to use the central limit. X bar is going to be the same for the groups as it was for the individuals. The one thing you're going to change is the standard deviation. So your standard deviation for groups is not going to be the same as it was for the standard deviation for individuals. What you're going to do is you're going to take your old standard deviations for individuals and you're going to divide it by the square root of n, where n is your group size. Okay? So just make sure we understand, it says important down here. Normal distributions, like a regular normal curve, like you did last time, applies to individuals, like you're picking one person, or you're picking one IQ, or you're picking one tire, okay? Central limit applies to groups. I'm picking a group of 35 people. I'm picking a group of 5 people, okay? And the group, anything bigger than 1 is considered to be a group, okay? So let's go talk about how the problems would look and how we would work them. Okay. Look what this says. I want to kind of show you the difference in the two. IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. So we're going to find 2 different probabilities, one for an individual and one for a group. So A says, find the probability that a person, one person, has an IQ greater than 110. Okay, this could have been on your last homework assignment. Okay, so remember what your step 1 was. You drew the picture of the normal curve, and then you shaded the area that you're looking for. So you want the person to have an IQ greater than 110. So remember, on that normal curve, the mean goes in the dead center, mean of 100. 110 is bigger than 100, so it's on the right. And I shaded to the right because it says greater than. So remember, once you get your picture, the calculator did all the work last time on normal curves. You went to second theirs, found normal CDF. And then remember, this is the left endpoint of your shading, 110. This is your right endpoint of your shading. That's your mean and your standard deviation. Now, like we talked about last time, I'm missing a right endpoint, so I had to fool the calculator. Nobody's going to have an IQ above 9,999. So I put all that in the calculator, hit enter, and remember, I want probabilities to be 3 or 4 decimal places. So number 1 is just like you had for homework last time. But now look at what number 2 would say. All right, so it would read, IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. Find the probability that a sample of 25 people has a mean IQ greater than 110. So not one person, but 25 people. All right, so that's how I know it's central limit, because I've got a group. I've got more than one. So my mean for the group is going to stay 100. So I still have 100 in here. All right, I want the probability that it's greater than 110. So my 110 is bigger. I shaded to the right because I said greater than. So the only difference between working problem 1 and problem 2 is the standard deviation. I can't use the same standard deviation that I use for individuals. So remember what we said, it's that old standard deviation of 15 divided by the square root of n, your group size. Remember, we were picking 25 people. So the square root of 25 is 5, and 15 divided by 5 is 3. So when I work this problem, my standard deviation is not going to be 15, it's going to be 3. Notice the pictures look the same. Excuse me, the only difference is the standard deviation. It's still normal CDF, left endpoint of your shading, right endpoint of your shading, mean stays the same, but the difference is my standard deviation is 3, not 15 like it does here. So notice my average came out, my probability came out to be much smaller. Now think about why that kind of makes sense. An average IQ of 110 is above average. So if you think better in percents, there's about a 25% possibility that if I grabbed one person, that one person would have an IQ above 110. But it would be highly unusual if I grabbed 25 people and their average IQ was bigger than 110. That would basically mean that I grabbed a bunch of people who had high IQs. And if you're grabbing a random sample, you'd expect some of them to be below. Okay, so that's why that's less than 1%. Now remember, in your book, when it asks you if something is unusual, it's unusual if your probability is less than decimal 0.05. And that number is way less than decimal 0.05. So the only difference when you're working central limit is that you have to change the standard deviation. Now, remember I said group size is bigger than 30, so why is that group size 25 and it's okay? Remember what I also said, if you know your original data is normally distributed, your groups can be any size. So a group of 2 or 25 or 200 will be okay. All right, let's go look at a couple more problems just to make sure that we're good before you try your homework by yourself. Okay, all right. Let's see what we got here. All right, Coke cans are filled with a mean of 12 ounces and a standard deviation of 11/100ths of an ounce. If 32 cans are randomly selected, what's the probability that their mean is at least 11 97/100ths ounces? Now, notice what I'm thinking about. It doesn't tell me whether the original data is normally distributed or not. So that's the reason that it's good that I have 32 in my group, because if I'm not sure if my original data is normally distributed, my group sizes have to be bigger than 30 for central limit to apply. So the way that I know that this is a central limit problem and not a regular normal curve problem is because I've got more than one. I've got 32 cans, okay? So to work the problem, the only thing I do is change my standard deviation. I take my old standard deviation that they gave me in the problem, and I divide by the square root of my group size 32. So when you take 11/100ths and divide by the square root of 32, you get about this number. Now, I'm not going to fuss about where you round the standard deviation to. I'd go to at least one more place of accuracy than my original standard deviation. So it was 2 decimal places, so that's kind of why I went to 3. Now remember, we're not rounding up, we're rounding off, okay? So now I do regular, it's like a regular normal curve problem. I draw my picture and I shade the area I'm looking for. So the mean goes in the dead center. Remember, the mean stays the same, okay? I want to know that it was at least 11 97/100ths. Well, 11 97/100ths is smaller than 12, so it's on the left. Now remember, at least doesn't mean less than. At least means that number or bigger. If you have to have at least $10 to get into the movie, you can't walk in with a 5, but you can walk in with a 20. So I've shaded to the right. And then remember, it's like a regular normal curve problem. Normal CDF, left endpoint on your shading, right endpoint on your shading, mean, and standard deviation. So the only difference is I had to change and get a new standard deviation. And then that ends up being my probability. Okay, so again, go to 3 or 4 decimal places on your probability. Okay, let's look at another one, make sure we're still okay. Quarters are manufactured so they have a mean weight of 5 67/100ths grams and a standard deviation of 62 thousandths of a gram. And that's actually real data, okay? So if you pick 40 quarters, what's the probability they have a mean or average weight between those two numbers? Now, is this a regular normal curve problem or central limit? Well, it's not a regular normal curve problem because it doesn't say that the data is normally distributed. And it's not a regular normal curve problem because I'm not picking 1 quarter, I'm picking 40 quarters. So remember, groups defined as more than 1, okay? And I need that group size to be bigger than 30 because I don't know that my original data is normally distributed. So remember, the only difference though is change your standard deviation. So your mean stays the same as it was in the problem. My new standard deviation is my old standard deviation that they gave me divided by the square root of my sample size. And again, since they went 3 decimal places here, that's why I went 4. Now, don't round to the end. So don't get the square root of 40 on your calculator and round that off and then divide. Just type in that number divided by the square root of 40 and round at the end. Now, I did this one to show you something. All right, so the mean goes in the dead center. I wanted the probability that was between 5.55 and 5.79. So those are on my picture, and I've shaded between because it said between. So I go to normal CDF. I do my left endpoint of my shading, my right endpoint of my shading, my mean, and my standard deviation. Now, remember I told you that I didn't want you basically round into 0 or 1, but you can't really control what the calculator does. Now, remember what this probability of 1 means. It means it's certain to happen. Now, in reality, this is not certain to happen. It's just the calculator has gotten decimal and a whole bunch of nines and is rounded to 1. But you better put approximately equal to. That warns somebody that that's not exactly right. So if your calculator rounds off to 0 or 1 when you're doing normal CDF, that's okay, right? Because you can't really change how the calculator rounds. So go try that homework. You should be fine. It's super simple. So step 1, draw the picture, the normal curve, put the mean in the center and shade the area you're looking for. If it's one person, it's a regular normal curve. If it's a group, if it's more than one, it's central limit. And the only thing you do is you change your standard deviation, then you work it like a regular normal curve problem. Okay, so I think that's super simple, so you should be fine. If you have some problems with it though, email me, okay, and we can set up a meeting.